Hello and welcome to the Unit 3 Section 4 video on solving quadratics by taking square roots. So in the last section we talked a little bit about simplifying radicals, and now we're going to take some of what we learned in simplifying radicals to use in these techniques that we're going to be moving forward in sections 4, 5, and 6, because there will be some square roots involved. So we will need some of those tools that we learned in section 3 to do this. So before we get into the technique of taking square roots to solve a quadratic outright, let's talk a little bit about quadratic versus linear equations. By now you are very familiar with the standard form of a quadratic equation. Each term of a quadratic equation is described by its characteristic when graphed. So this first term that we have, the ax squared term, well, this is our quadratic term. The bx term is our linear term, and the c term is our constant term. So each one of these gives us a certain characteristic of our quadratic. So let's say that we got rid of one of these terms. Okay, let's say we got rid of the ax squared term. If we don't have this quadratic term, then we no longer have a quadratic equation, because this quadratic term is what makes a quadratic equation quadratic. A quadratic equation is an equation that has a squared term, and that's the highest order term in the equation. If we didn't have the squared term, all we'd be left with is bx plus c. And if all we had was bx plus c, it would not be quadratic, it would instead be linear. Because that bx plus c is essentially your slope-intercept form. You remember y equals mx plus b, where m is your slope and b is your y-intercept? Well, that's essentially what you're left with, bx plus c, where here b would be your slope and c would be your y-intercept. If you think back to Unit 2, how did we find our y-intercept in a quadratic? In a standard form. It was our c term, right? Because if we set x equals to 0, we'd be left with c. So you can kind of see how all of this starts to connect together a little bit. All right, when we solved linear equations, you may not have been aware of this, but you were doing the order of operations backwards to solve for your variable. So you may remember your order of operations, PEMDAS, or please excuse my dear Aunt Sally. Well, now we're going to work it backwards, which happens to be SAD MEP. I kind of put it that way, SAD MEP, because that is PEMDAS backwards, and it is our order of operations backwards. So you remember S stands for substitution, or actually I should say subtraction. S stands for subtraction. A stands for addition. D stands for division. M stands for multiplication. E stands for your exponents, which I'm just going to write as exponential, your exponential terms. And then P, it stands for parentheses. All right, so let's think about this. Let's do a little example over here on the side. So you remember back when you were doing the order of operations, say in Algebra 1, and you had an equation, say y equals, or actually let's say some number. Let's say, let's just do something simple. 3x plus 5 equals, let's say 2, okay? And we want to solve for x. What was the first thing we did? Well, we subtracted 5 from each side. And that happens to be the first thing on our order of operations backwards. So you get 3x equals negative 3. Then what did we do? Well, to get x by itself, we had to divide each side by 3. And that is the second thing we did. And you notice we've gone down the order of operations this way. And so we were left with x equals -1. So you may not have been aware of this, but we were doing the order of operations backwards. Okay? If we wanted to get rid of something that was added, we had to do the inverse of that and subtract. If we wanted to get rid of something that was multiplied by the x, we had to do the inverse operation and divide. Well, the inverse operation of squaring a number is taking the square root. So therefore, we're going to use square roots to solve a quadratic equation because we do have an x squared term, and we're going to have to get rid of that square on the x to finally solve for x. So now let's talk about the actual technique of solving a quadratic equation by using square roots. We're going to do this by looking at two different methods or two different situations where we can do this. The first is when we don't have a linear term in the middle, okay? So we don't have that bx, we just have x squared and maybe plus or minus some number, and it's going to be equal to 0, okay? Or at least we'll eventually set it equal to 0, or it may have the number already on the other side. The whole point here is we're trying to solve for x. Okay, so remember, every positive number has two square roots, a positive square root and a negative square root. All right, the reason for that is, what is 2 squared? It's 4. What is -2 squared? It's also 4, because anytime you square a negative number, you're multiplying it on itself, and a negative give you a positive. So that's why when you take the square root of 4, it's going to be plus or minus 2, because 2 squared is 4, and -2 squared is also 4. So let's do a few of these examples. And let's start off with a few easy ones. So in example A here, we have x squared equals 81. So to solve this, we're going to take the square root of each side. And when we do so, we're going to end up with plus or minus square root of 81. Okay? Square root of x squared is going to be x, and the square root of 81 is 9, so it's going to be plus or minus 9. So your solution is either positive 9 or negative 9. All right, for the next one, same thing. We're going to do the square root of each side, and we're going to end up with plus or minus square root of 67. Well, the square root of 67 cannot be simplified. So our final answer is simply going to be x equals plus or minus the square root of 67. All right, for C, we've got the square root of x squared on this side. We've got the square root of 32 on this side. And don't forget your plus or minus. Square root of x squared is x. Now, we can simplify the square root of 32, because the square root of 32 is 16 times 2, 16 being a perfect square. We went over how to do that in the last section. So we have x equals plus or minus, pull your 16 out, square root of 16 is 4, square root of 2. And that would be your answer to this one. All right, let's do a few more of these. The square root of x squared equals the square root of -9. Well, we know the square root of x squared is x. Square root of -9, we know the square root of 9 is 3, and then we have the negative in there. And remember, when you take the square root of a negative number, you're going to be pulling an I out. So we have an imaginary solution. Now, this is not absolutely correct, because what did I forget? I forgot to put plus or minus on my square root. So your answer is not going to simply be 3i, because remember, when you take the square root, you're going to have two numbers that are answers in most cases. So instead of just 3i being your answer here should be plus or minus 3i. All right, for the next one, again, we're just going to take the square root of x squared. Here we're going to have plus or minus the square root of -41. So the square root of x squared is x. square root of negative 41. Well, can we simplify the square root of 41? The answer to that is no. But we can pull out our negative 1. And so our final answer is going to be plus or minus I square root of 41. All right, for the next part, we have square root of x squared equals the square root plus or minus the square root of negative 28. So x equals, can we simplify the square root of 28? We can. That breaks down into 4 times 7. And then we have our square root of negative 1 out here on the side. And so our final answer is plus or minus square root of 4 is 2, square root of negative 1 is I, and then you've got square root of 7. All right, in the next row here, we have some examples where you're going to have to do a little rearranging before we can take the square root. So for this one, we've got to divide each side by 5. Remember, you've got to do your order of operations backwards, and we've got to isolate that x squared term before we can take the square root, because in the order of operations, exponential comes second in PEMDAS, but it's next to last when you're doing SATMEP, okay, when you're doing those order of operations backwards. So we got to divide by 5 first, and when we do, we get x squared equals 16. And now we can take the square root of each side. You've got the square root of x squared equals plus or minus the square root of 16. So x equals plus or minus 4. For this next example, we need to get x squared by itself, so we're going to add 9 to each side. So that's going to give us negative 5 on the right-hand side. Take the square root of each side. Get plus or minus the square root of negative 5. And then we have x equals plus or minus, I comes out from the negative, and we can't simplify the square root of 5. And then for this last example, in this set, we have 5 that needs to be subtracted from each side. So we'll do that first. That's going to give us 36. Then we divide each side by 3. So 36 divided by 3 gives us 12. Now we can take the square root of each side, plus or minus the square root of 12. X is going to be plus or minus. Can we break up the 12? We can, into 4 times 3, 4 being our perfect square. And so our final answer here is going to be x equals plus or minus 2 square root of 3. So you've seen how easy it is, especially when you just have an x squared. You take the square root of x squared and you just end up with x. And this is when we do not have a linear term. Now there is a case where you could have a linear term and it's within a different form, because we've been talking about standard form here. Well, let's go back and talk a little bit about vertex form. So the other form where you can actually solve an equation by taking a square root is if it's in vertex form, because recall the vertex form. You've got a times the quantity x minus h, quantity squared, plus k equals 0. Well, you'll notice that you only have one x in here, and that x is within something that's squared. So since that x, the only x is within something that's squared, then we can use taking the square roots to isolate our x. So let's do some examples of that. Okay, if you're given vertex form, then taking the square roots is going to be a good method for solving these. So let's start with example A. We have x plus 4 squared, quantity squared, equals 25. All we have to do is take the square root of each side, since the square is already isolated by itself. Okay? So you take the square root of each side. That's going to leave us with x plus 4 on the left-hand side. On the right-hand side, we have plus or minus 5. And then we're going to subtract 4 from each side. Because remember, this x plus 4 was in parentheses. And parentheses is the last thing we do. And so what was in the parentheses is the last thing we're doing here. So we have negative 4 plus or minus 5. Now, that's all well and good, but we can do better than this because these are just numbers. You got negative 4 plus 5, negative 4 minus 5. So here, let's just go ahead and write our solution set. We can go ahead and just say what the values are. Negative 4 plus 5 is 1. And negative 4 minus 5 is negative 9. So our two solutions are 1 and negative 9. For the next example, you've got a 1/4 out in front, and then you have your squared and things in the parentheses. So let's start with multiplying. We're going to multiply each side by 4. And that's going to give us x plus 3 on the left-hand side, quantity squared, obviously, equals, multiply 4 times negative 9, that's going to give you negative 36. And now we're going to take the square root of each side. X plus 3 quantity squared, plus or minus the square root of negative 36. And so we get on the left-hand side x plus 3. On the right-hand side, we get plus or minus 6i. And then we subtract 3 from each side. And I'm going to stick it out in front. And that's our final answer, negative 3 plus or minus 6i. Now here we're not going to split it up because you can't combine that real and imaginary number. And if we were to split it up, it would just be negative 3 plus 6i and negative 3 minus 6i. I don't really see the point in writing essentially the same thing twice, once with a plus and once with a minus, when we've already gotten it written in about the most efficient form you can here. So this would be an acceptable answer for this problem. And just remember, this is two solutions, one for plus, one for minus. All right, for the next one, let's add 4 to each side. So that's going to give us x minus 7 quantity squared equals negative 27 when we subtract, or when we add 4 to negative 31. So we're adding 4 to each side here. Then we're going to take the square root of each side, plus or minus the square root of negative 27. So we've got x minus 7 on the left-hand side. We can break down the square root of 27 into 9 times 3 because 9 is a perfect square. Then, of course, we still have our square root of negative 1 over on the side. And then we're going to put it all together. Add 7 to each side. So we've got 7 plus or minus, square root of 9 is 3, square root of negative 1 is I, square root of 3 is still square root of 3. So your final answer is 7 plus or minus 3i square root of 3. All right, for D, we have to add 5 to each side first. So 8 plus 5 gives us 13. Then we're going to divide each side by 2. Don't let the fact that you're going to end up with a fraction discourage you. Just do what you know you have to do. Because now what we have to do is take the square root of each side. But thanks to the last section, we know how to handle a square root of a fraction. And we're going to handle that by rationalizing it. So let's go ahead and simplify the left-hand side. Take the square root of something squared, and that's what's left, x plus 2. On this side, when we rationalize it, we're going to multiply the top and the bottom by the square root of 2. That's going to give us a square root of 26 on the top and 2 on the bottom. And then all we've got to do is subtract 2 from each side. And that gives us our final answer, negative 2 plus or minus the square root of 26 over 2. Doesn't look pretty, but that's our answer. All right, for E, we're going to divide each side by 3. So we've got x minus 2 squared equals 40 divided by 3. We're going to take the square root of each side. And again, we are going to rationalize the right-hand side. Go ahead and simplify the left. Rationalize the right. Square root of 3 times 40 gives you the square root of 120. Square root of 3 times the square root of 3 gives you 3. And then we can simplify what's under that square root. So let's go ahead and add 2 to each side. Square root of 120, we know that 4 will go into 120 because 4 will go into 12. And when we take the square root of 4, that gives us 2. And that leaves us with 30 under the square root over 3. So our final answer is 2 plus or minus 2 square root of 30 over 3. All right, for this final example, we've got to divide each side by 16. So we'll start by doing that. 49 over 16. Then we've got to take the square root of each side. So you take the square root of the squared term, take the square root of plus or minus the square root of 49 over 16. So you end up with x minus 2 on one side. On this side, we end up with plus or minus square root of 49 is 7, square root of 16 is 4. So when you can take the square root, just go ahead and take the square root. No need to rationalize this one. And then we add 2 to each side. But these are both just numbers. 2 and 7/4 are just numbers. So if you were to find a common denominator, which I'll write that over here on the side, 2 is just 8 over 4, plus or minus 7 over 4. So we can get our two values for x fairly easily. They're both going to be fractions. 8 plus 7 gives you 15 over 4. And 8 minus 7 gives you 1 over 4. So your answers are 15/4 and 1/4. Okay, so that does it for this section. This is a little bit of taking square roots. The two situations where you can take the square root of each side is when you do not have a linear term, so you only have an x squared term. Or if you have it in vertex form where the x is within something squared and there's no other x terms lying around. Okay? So just keep in mind those are the two specific situations where you can do this. In our next section, we will start to explore other situations where we can use square roots, but we have to do other things first, and that other thing would be completing the square. We're going to have to make something work for us. So that's coming up in the next section. For now, that does it for this.